Today, we will talk about the link analysis and the web page ranking, meaning that the graph information that is provided within the code of web pages, the HTML code, provides us very important information that is complementary to the other information like full text and other content. So today we are concerned with the graph of the web, and in the sense that we are only concerned by the graph. So we will consider the web pages as nodes and the links between them as edges, oriented edges. We'll call them links, as the terminology is used in the community. And we will talk about generally the web graph, and basically about the native management or native processing of graph and detections of subgraph and fragments in the graph that could directly be interpreted as some unique feature or community or something that exists also in the real world. So something semantic, but based on the graph structure. And then the larger part of the talk is about of the ranking based on the statistics of the links between the nodes, between the web pages, and basically this will be about the PageRank of Google that Google developed some 22 years ago. So we start with the general term of link analysis. Okay, so we get back to the 1998 when the focus was put on the possibility to use something else than just content. So the web pages are no longer reduced to a collection of full text, which is the traditional information retrieval interpretation, but also the structural information suddenly appeared quite useful and in some sense necessary for web search engines. And this is the advantage of Google's technology, the PageRank, that proved that. Okay, so why it came to this level, or what was not okay with full text? So until the 1998, we had just purely full text search engines where content-based queries were somehow processed based on cosine measure or Boolean model, whatever. But at that time, we realized, or the companies that developed search engine realized that the full text search alone is not enough. This is the consequence of the web pages or the web world, because it is something completely different from the environment we experienced in 70s with the digital libraries. Because in digital library or library in general, we have quite a controlled quality of resources. So in library, what we have in library, we have books, we have journals, we have reviewed stuff. So we cannot basically retrieve information that is either false or very low quality or even illegal. But this changes when we take the technology developed for digital libraries and then just put it into web search engines. Because on the web, everybody is a producer of documents, right? So it is very cheap to produce a text document and just embed it into a web page and publish it. So there are not only high quality documents, but also spam pages or even illegal forms of advertisements or even models for getting information, stealing information from people. So here we cannot be just okay with the content-based search, because also the low quality documents and the spam documents contain the relevant keywords that the vector model and Boolean model are based on. So we must also take into account something that is reputation or trustworthiness or something like that, popularity maybe, that allows us to filter out the garbage from what we really need. But how to do that? Because if we just expect this kind of information related to the popularity or high quality content is embedded within the document itself, within the web page, that this is not a solution, because we can easily fake this information. This is something that that is carried, that would be carried inside the document itself. So we need some external information that is objective and cannot be so easily faked. And well, what we have, that's the graph, that's the web graph. And the really important factor of analyzing web graph is the statistics on the inlinks, so-called. I will talk about inlinks and outlinks later. Okay, from the information point of view, the most voluminous information, of course, is the content. The full text is probably 90% of the volume of the information inside a web page, and there is just a few links. So it seems that the few links is not much improvement on the information. But basically, this is misleading because the link is compact, but is very explicit and brings rich information because it connects two pages together. So we basically can view the link as a way to another rich information inside another web page. So the whole graph is something completely different than just a collection of texts, because it is one huge system of documents, not individual instances of independent documents. So when it comes to the reputation or the popularity or whatever term we choose, we basically ask a question, not only what is inside a web page, inside the document, but also what is the context. So who is our author, or what is the company that produces these documents? What is the popularity of the author, not just of the web page alone. Of course, we are only concerned by popularity of web pages in link analysis, because the infrastructure is quite low level at the web level, so we only have the possibility to rank web pages themselves. We don't have any data model for producers and data and so on the level of web. Of course, we have these on higher level abstraction, like social media. In social media, we don't have only low-level web pages. We have users, we have posts, we have many data types. So, and also we have external, and it's closed, so we cannot just fake somebody's number of likes, for example, because this must be done externally. But here we are still in the low level infrastructure of web, so there are only web pages and links between them. So if we have just these conditions, what we can do in terms of determination of popularity or importance of web pages. So the answer is the link analysis, of course, it's based on the graph algorithms and the graph discovery, basically. So what we can do, we can directly discover web communities as some patterns in the graph, but we can also just compute statistics on top of the graph properties, basically doing some analytics, doing some aggregation, and augment existing search engines by these new statistics to better filter out spam or garbage pages, or generally low quality information. And third, we can also use link analysis to provide some visualization support for a user that is involved in analytics, in data science, for example, to better understand and iteratively process graph-based information, for example, a part of the web space in this case. When we talk about web, we still think for this topic of a web that is quite pioneering stages. So we have just a collection of rather static pages. We will talk about documents. So we still have documents, and on top of just the full text information, we have also links between the documents. So for us, the best example for this is Wikipedia, because Wikipedia appears quite old-fashioned web. It's just pages about topics that are interlinked, and on the left side we can see the graph, the simple representation of what we actually can see in the web browser, but what we need to know is this graph information. So we have nodes. The nodes are the pages. We have directed edges. That's the links, the hyperlinks, and that's it. So that's the only information that we will use in this lecture. Now, the directed edge in the graph, also we are talking about links between pages or between the nodes, can be viewed from two perspectives. First, as in-link or out-link. So let's focus on this red edge. That is for the node 2, it is in-link, but for the node 1, it is out-link. Of course, it's obvious from the terminology. It's out-link, it goes outwards, and here it goes inwards. So we have two interpretations of the same link. But it's not so symmetric as it appears. So because outlinks are represented directly within the code of the web page. So in the HTML code, we have the well-known element A with href, some URL, and something that should be displayed. And this is something the creator of the web page can produce. So the number of outlinks is easy to count and easy to produce. The outlinks are easy to produce. But in links, that is something completely different, because in links are not stored within the web page, but in other pages for which the links are outlinks. So it is first not easy to count at all, and most importantly, it is not easy to create for that web page. Everybody wants to have many inlinks, because if a page has many inlinks, it basically means it is popular. That it will follow in the later discussion. But this is the situation. It is not symmetric. Outlinks are easy to create and count. Inlinks are not easy to create and count. And to provide the numbers for the inlinks, we basically need some external service that uses kind of index that we can use for counting. We cannot just count it by ourselves or with no support. So Google, as a major search engine and indexing engine, supports this service. If we enter into the text box of Google, search statement like link, double colon, and the URL of the page, we basically get the results, and we also get the number of the inlinks. So for example, here we want to know how many inlinks there are for the URL www.harvard.edu, and we get some response, and of course not precise, but it gets us something like 4,000 results. So the number of inlinks for this just simple high order URL Harvard is 4,000. We also get the results. What are the pages that link to this other to the Harvard page? We can really inspect that most of them are basically pages that are within the Harvard Edu domain. So basically there are some internal links, but also here is one from different domain, here is different domain, and here is different university. So this is how we can get the statistics on inlinks in practice. And now, what are the basic patterns or fragments that we can get or we can observe within the web graph or within any graph that is directed? We will just introduce the terminology that is basically intuitive. So first, hub. A hub is a node or a web page that has many outlinks. So that's the name. So hub basically means this is some resource that basically probably contains some condensed information on many topics and provides links to other pages that maybe detail these topics. So that's why hub. Authority is different concept. So there are many inlinks, and it means, okay, there are many other pages that refer to this page. So for them, it is authoritative page. So we have a node or a web page that is basically important. And the combination of the two is a node that has many inlinks and many outlinks. And so it could be both hub and authority together. And this could be maybe the case of the Wikipedia pages, because if I have a highly relevant, I have a web page basically on some high level topic, for example, on the biology, for example, subject. I have many pages that detail the subject of biology, and I also have many other pages that refer to the concept of biology. So from this point of view, it's both hub and authority. When talking about slightly larger fragments that include more than just one node, we get several other concepts, fragments like page endorsement. It basically is very basic concept that one page refers to other page, so it endorses the page. So it's a very, very low level concept, but we are building up. And mutual endorsement is called as relevant pages. So if we have both one page endorsing the other and the other endorsing the first one, we have relevant pages, and they are kind of symmetrical because they refer to each other, so they should be on the similar level of importance and also semantics maybe. But we know nothing about the content of the nodes. We just now look on the edges, on the topology. Then co-citation is a page that refers to several other pages. So this fragment basically says, okay, these pages are co-cited by some other page. So they are not connected together, but transitively they are somehow relevant because there exists another page that co-cites these two pages. So from this point of view, there is some relation between these two. The opposite is social choice, and again, because two pages refer to the same page, they again are somehow similar from some reason. And then there is also transitivity involved in all of these fragments. So the first one is transitive endorsement, just transitive. This type and it just says, okay, I can transitively induce that this page endorses also this page through some middle page. And now we get into more complex shapes that could represent web communities because they are complex enough to have some meaning in the real world. So very important type of graph or subgraph is bipartite graph. Bipartite graph means we can observe within the graph, or we can just define a graph where there are two sets of nodes. One set we can maybe see the nodes in the set as objects, and the other set that we maybe can see as subjects. And let's say this could be a community. So there are many users or many individuals in a community that share many interests. So, for example, if we have a community of programmers and their interests are programming, databases, and graphical design, for example, so we can observe that many of the users talk about the same topics. So that's why they form a bipartite graph. Of course, this is just one way. There are no links from the second set to the first set because it's basically different type of the nodes. So they cannot just refer anywhere. But from the web graph point of view, we can also interpret this subgraph that has a form of bipartite graph as a web community sharing interests. Remember that everything that we are discussing here as web pages could be higher level entities like profiles on Facebook, like posts on Instagram, whatever we can imagine, and that the edges are not just real edges, but they are just some logical connections that are directed. For example, if this is page on Facebook, for example, and this is user, then this page is liked by this user or is commented by this user. We can have different types of these edges in the contents of Facebook. But now we are just limited to the very basic structure of directed graph, but we can really use this low-level view of graph-based analysis to the high-level concepts like social media. Okay. Second is entry, and basically this is the generalization of the social choice. And as I said, the transitivity in the graph is a very natural thing. So if some pages simultaneously refer to a common other page, it's the social choice. And if we have a hierarchy of these social choices, we get entry. And we can also see this as authority, even that it has only 3 in links, but if we take the whole hierarchy of the entry, we can basically compute that it is many more. It's basically 8 in links when including also the next level here. So we have hierarchical authority. The other way around is outtree. So we have some very high-level hub that refers to other pages, and some of the other pages refers to other pages, and so on. So basically we have the same as entry, but the opposite. We have generalized co-citation, and basically we get something like hierarchical hub, because this is something that is on top of the hierarchy. Then a very interesting graph fragment is a k-connected component, or just 2 connected component. The 2 connected component means that if we remove any of the nodes in the component, it still stays compact. It still is one component graph. It doesn't disjoint. So, and if we have k-connected components, it's for larger numbers. From the semantic point of view, this could mean that this is a community of something, users, resources, pages generally, that are some peer-to-peer community. It's basically something like relaxed complete graph. We cannot experience many complete subgraphs in a graph because complete graph means everything is connected with everything. But k-connected component is something similar to complete graph. It's not so complete, but it's still strongly connected. And the last fragment I want to just show here is a cycle that's quite a weak structure observed within a graph, because it could be really discovered in very many instances in the graph. But still, it could be recognized as a community. For example, in the early ages of web, in 90s, the cycles, or also called web rings, were quite commonly used arrangement of personal web pages that basically allowed to create community. Because, for example, if we have a community of game players, they could refer to the next one. Each player can refer to the next one, and when we browse home pages of game players, we can basically browse all of the pages of all the players and then return to the first one. So this is something that had a sense in the early ages or early years of the web as such, and nowadays it has also sense, but not on the level of individual web pages, because that doesn't make much sense. But it could make sense in a higher level in architectures, like in the social media. If we limit the type of the node, for example, to commenting, for example, user comments on some other user, and this user comments on some other user, and so on. So there is some filter on the edges. Then we can get something that is semantically meaningful. It's not some edge, but it's some strictly limited type of edge, and then we have strictly limited cycle in the semantics. Okay, so this was cycle. And now the last purpose that we have announced is the visualization, where we can use the analysis as a support for users. So this is quite a primitive visualization, but still I can see that we have some arrangement of nodes that are connected together. So this is basically this is a real web subgraph. And this is some website of some municipality, and the nodes, of course, are web pages, and the edges are links between the web pages. And the graph of the edge is not just some real distance. It is the color scale means we have more information in this graph, not just the topological information, but we have also information about the full text similarity of the web pages. So as you can see on the scale here, on the legend, very dark colors means very high similarity, and lighter and red and orange and yellow colors mean very small similarity. So you can see that in the graph, most of the colors is basically small similarity. There are many of yellows, many of orange, some red, some light green, and only a few dark green like this one. That means basically that these two pages, this one and this one, are not only connected, but also similar with respect to cosine similarity of the full text of the pages that they contain. So we can use graph structure also for analytics. Okay, and basically, by the way, this is just two connected component with 134 edges. So it's not any subgraph, it's just two connected component. Okay, now we are in the second part. Now we leave the topic as just playing with the subgraph structures, but we want to resort to counting basically in links and also outlinks, but mostly in links, that would provide us with the statistics that could be interpreting as a measuring popularity or relevance of web pages or trustworthiness or basically some ranking of web pages. This topic is nothing very new. It certainly didn't appear with the web. It existed in quite a long history. Basically, there exists a science branch that is called bibliometry or scientometry, and basically it's very, very similar to what we are going to compute or to do, because if we have scientific publications like books and journal articles and computing of so-called impact factor of journals, then basically we are using something very similar to what PageRank is computing for web pages. But the web pages are not scientific articles, but the inspiration is in bibliometry. So in general terms, the PageRank with small p will stand for a non-negative real number that represents the popularity or the rank or the significance of a web page on a global scale. It is not dependent on any query. It will not be dependent on any content within the page. It is just computed from the structural information, that's mean from the graph. So from the numbers of in-links and outlinks of that pages. And based on this concept, there appeared basically two competing algorithms in the 90s. One was PageRank, that basically was the reason that Google really won among all of the search engines. And the second was HITS. And they both are kind of similar in what they want to compute. Here the PageRank with capital P means the Google PageRank. Here we have the small letter as a general PageRank, whatever algorithm. Here it is really a trademark of Google, so PageRank here. So it is also patented. Okay, so before we proceed to the PageRank, we conclude this ranking part, or we just announce why we are doing the page ranking for search engines, because we are not doing this just as a separated task, but we are doing page ranking because it would help us with improving ranking that we already have. So we basically have ranking, basically, for example, based on the vector space query and cosine similarity, the bag of words we already discussed last lecture. And we can improve the ranking by content using page ranks we get independently for the pages, and we can, using these page ranks, filter garbage from what is respected. So we combine both of the rankings and aggregate the result into a final ranking, and that's the ranking that the user gets from the search engine. So let's have this example. We have 6 pages. Based on the content, we get these scores. It's sorted. So the most relevant with respect to some vector query is the page 3 with score 0.9. and these are decreasing. And then we have page ranks that are independently obtained for the same set of pages. We have the same set of 6 pages. And we can fuse or aggregate these two partial rankings into the final ranking and get the final score. Of course, the aggregation could be done in a number of ways. We can just add, for example, for P6 we have 0.73. Here we have for P6 0.55. We can just add two numbers or do average or take the maximum, minimum, whatever we want to do. So that's the aggregation, and then we have the aggregated scores, and this is the final result. We can see, for example, the P6 page 1, even though it was not so good for the content ranking, it's 4th, but it's quite good with respect to the overall popularity, which is modeled by the PageRank. So because of the two factors, it basically got the first place. Because P5 was even worse, and it didn't really beat P6. And here P3, that was really highly relevant with respect to content, was 4th with respect to the PageRank. So it dropped in the order to the 2nd place. So this is about generally aggregating particular rankings of the same set of elements, web pages in this case. Okay, and now we proceed to the PageRank. So PageRank is guided by a simple thesis that is just one sentence, and the sentence sounds: web page is important if it is pointed to by other important pages. So it's basically cycle definition that says I'm important if other important people refer to me. So okay, but even that this means is a cycle and does not make any sense. It could be formalized, and we can make sense from this. And the hits thesis is the other PageRank, basically, is more complex because it distinguishes not two web pages, but it distinguishes between hubs and authorities. So a page is a good hub if it points to good authorities, and page is a good authority if it is pointed to by good hubs. So we have here some basically complementary definition, but still it is again cyclic, circular definition, because something is good if it points to something that is also good. So what's good? Again, it could be formalized, but we will not discuss hits. We will only discuss the PageRank, but it would be similar also in the case of hits. So the original formula of PageRank is very simple. It's basically a formula for computing the PageRank, which is the function R here, for a page PI, and it's computed as a sum of PageRanks of pages PJ, which are pages that basically link to the page PI. So for PI, all of the inlinks of PI lead to nodes, and these nodes are the set of BPI. So we take all of the nodes PJ that refer to PI, compute their PageRanks, then normalize their scores by the number of their outlinks, and there we sum it, and that's the PageRank. Okay, what we are doing here, the division by the number of outlinks, it's because we can have very different pages PJ. We can have just a very simple page, short page, where there is only just one outlink, and the outlink is the link to PI. That's why it is here. And in such case, the score of this PJ is much more relevant to alter also the score of PI than another page for which the PI is just one of many pages that this page refers to. So for example, if we have a hub in this place, a hub is a page with many outlinks, then the PI that is referenced by the hub is just by one of many. So if this is important, it should be also reflected in propagation of importance of this page to importance of this page. So that's why this is divided, basically normalized. Yeah, this is something like in the case of TF-IDF we had in the vector space model. Also we had their normalization because in some documents there were many of terms, and in some others there were just a few terms, that there was also normalization to really make different documents comparable. Here we are doing comparable different pages, not in the perspective of terms statistics, but outlink statistics. Okay, so we have the original formula, but the problem, of course, is we cannot just use directly this formula because we are computing PageRank, but we are using another PageRank for computing that, and that's the circle definition we just have. Don't know these numbers, but what in computer science everything is easier if we can make it an iterative process. So we can just turn this formula into iterative version. So we have iteration k plus 1 that is relying on iteration k, and we need to also define the first or zero iteration. So for this case we need to initialize the PageRank of all of the pages basically. And to do it very simply, we can say all PageRank of all pages in the web will be set to 1 divided by n, which is the number of all web pages, and we can then compute the PageRank. So this is the way how to really compute the PageRank, but we don't know if this is okay because we initialize the PageRanks, and there are many questions connected with this. But before we discuss the quality of this formula, we show just one running example. The running example is this simple graph that is consisting of the 6 pages that we use already in the ranking. And these 6 pages are somehow referring each other. So we have directed edges between the nodes, and that's it. So if we want to compute all of the PageRank for all of the pages, then based on the iterative formula we just created, we can initialize in the 0 iteration the PageRanks to 1/6 because we have 6 pages, so 1/6 is the initial value of all of the PageRanks here. And then in first iteration we get to these numbers because we use this formula. In second iteration we get to these numbers, and now we stop and just say, okay, let's see what is the ranking after second iteration, and it's this. So we have first, so highest ranked page is P4. The second highest ranked page is P6, then P5, P2, and then on the two last positions is P1 and P3. And now we can ask many questions. But before we will ask the questions, we prepare for some more analysis, and we would like to transform the formula from this summation form into matrix form, because it gets more this is too fragmented formalism. It's better to just work with vectors and matrices. So basically this and this is the same. If we represent the inlink, the outlinks by, and inlinks of course, by a matrix, and that is square matrix between all of the pages. It's square matrix n times n. Then we can represent basically this component in the matrix. So if we have, for example, let's see here, page 3 has three outlinks, here, here, and here. And we have, for these three outlinks, the positions in the matrix occupied by 1/3. So here is to P1, here P2, and here P5. And we can do this for all of the pages we have here. We can observe that there is one page, P2, that does not have any outlink. It only has two inlinks. So we get this matrix H, and then the second component of this formula is a vector pi, which is basically a vector of all of the page rank of all of the pages. And we can reformulate then this formula into the matrix one. So here the k plus 1 iteration is here. It's the k plus 1 iteration of the PageRank vector, and we get it from the kth iteration pi multiplied by the adjacency matrix H. It's basically adjacency matrix, but normalized by, it's not just once there, it's normalized by the number of outlinks. Also notice that the matrix is very sparse. It's again similar as we already experienced in the Boolean and vector model, where we had different matrices. In vector and Boolean model we had term by document matrix, there were terms in documents. Here we have just square matrix, links from pages to the same pages, but still we have very sparse matrix. So in practice, again, we can observe something like a constant there, like let's say 10 non-zeros per row, up to, here we have only 3 maximum. And this is something that is again very similar to the Boolean and vector model. In Boolean vector model, we observe that every document is limited with the keywords it can contain. It does not scale to the whole vocabulary, mostly. And here it is even more prominent and visible that we have only a constant maximum number of outlinks that can appear in real web pages. So we surely cannot have a billion of links in if we have billions of pages. So basically we can see this super sparse matrix almost as a vector, because it has only 10 times more non-zeros than would have a vector, because really it's really sparse. And here are there are even only zeros. Okay, so this is some preparation for further discussion. But now we want to ask if this formula, doesn't matter if the summation-based formula or the matrix-based formula, is good enough to compute the PageRank. And the questions that rise are basically 6. First is, if this iterative process we just introduced is running indefinitely, or will it actually converge if the PageRank scores will converge? First question. Second question, if it does converge, how should the matrix H look like to converge? So for which H the PageRank computation is guaranteed to converge? Then if it converges, does it converge to what we want to? So does it comply with the PageRank thesis? So we really get high page ranks for those pages that should be highly rated, so the important ones. And next, if it converges to one PageRank vector or to multiple PageRank vectors. So I don't know. So maybe there are more PageRanks. So it's not deterministic process, but I would like to have deterministic process. 5. Does the convergence that hopefully exists there depend on the starting vector? So does it matter how I initialize the scores, the page ranks, or does not? And technical question, if it converges, how long will it take? Is it computable for practical task, or is it just really theoretical process that does not pay off? And for all of these questions, unfortunately, the answer is, well, actually, this is not sufficient. Just a few examples. Some of the problems, the highest problem that can appear when using this original formula is that there appear so-called rank sinks, which means that some pages basically steal ranks from other pages, and these pages that lost basically get 0 page ranks, and that's bad because then we lose ranking between the 0 ranked pages. You can see it on our example. This is still the same example, but we are proceeding from iteration 2 that we already inspected up to iteration 13 that basically results in this behavior in the rank sinks, because we can see that this set of pages basically loses all of the page ranks in favor of this other set of pages. So these, because of this edge, apparently this oriented edge, is the reason why all of these page ranks here basically flow to this segment. And basically what we get is 0 page ranks for these 3 pages and quite high page rank for these pages. And then we, if we recompute the positions of the pages in the ranking, we get P4 is first, P5 is second, P6 is third, and then all of the other pages are on the 4th place. So there is no other ranking between these ones. And this is bad because we want to have ranking and not this aggregated result. So this is the first problem, is rank sinks, and the second problem is cycles. That is kind of more artificial problem here in this example, but it could really happen. And it basically means that in the iterative process, we basically may not get into the end. So the process could not converge, and the cycle could result in so-called rank flipping. For example, if we have a very simple graph like this, just 2 nodes and two edges, and we have the 0 iteration pi vector initialized to 1 and 0, then in the iterations, these ranks, page ranks, will flip like that. So in the first iteration we get the opposite, 0, 1, and the second iteration we get the opposite, 0, 1 and 0, and so on. So there is no convergence, it just flips the ranks forever. And this is cycle. And this is unfortunately what the original formula does, or does not prevent. Okay, but what to do? And now it comes the real contribution of the Google's PageRank, because, okay, let's start with this original equation, but we want to get some better properties of this iterative process to really not have the rank sinks and so on. So the founders of Google noticed that this equation basically resembles a so-called power method in the theory of Markov chains, where the H is not adjacency matrix like for web pages, but it's generally some transition probability matrix H. But it could be applied also to web pages, because we can also see the matrix H as a transition probability matrix. Because what does it mean? If we are on page 3, where we can browse, where we can continue browsing, if we are a user that browses web pages. So we can go using the hyperlinks to page 1, page 2, and page 5. And we can do that based on the probability of the transition. And the probabilities here are basically the same, 1/3. So we can randomly choose 1, 2, or 5. So this is transition probability. And this could be used here. So we can just pretend this is a power method of Markov chain, and we basically need to secure properties for the metric H to be compatible with the power method. And that means we need to make this matrix H, or we need to use the matrix H to create some other matrix that will be stochastic, irreducible, and aperiodic. And if the matrix is or satisfies these 3 properties, then it basically will positively answer to all of the questions. There will be just one PageRank vector pi. It will not matter how we initialize the 0 iteration of the scores. It will always converge, and there will be no cycles or rank sinks. So all what we need to do is to transform the matrix H into some other matrix that is semantically equivalent, but is stochastic, irreducible, and aperiodic. Okay, so the first property is stochasticity of the matrix, and it's quite simple property. It says that a matrix is stochastic if the rows in the matrix sum to 1. And we basically have almost stochastic matrix H, because we already normalized all of the non-zero value in the matrix to 1 divided by the number of outlinks, which is the number of the non-zeros in the row. So we basically already have row summing to 1 in cases where there are at least one non-zero values in the matrix. But we also have rows where there are only zeros. We already had this in the matrix. Here we had this page 2 that has only zeros. So because of this, the matrix H is not stochastic. Otherwise it would be stochastic, but because of this 0 row, it is not stochastic. So what to do now? And it basically is some matter of interpretation. Basically, I need to say that we have 0 rows when we have so-called dangling nodes. So as the page 2 there in the example, we have pages without outlinks, and in practice, these nodes are those that basically cannot have any outlinks, like images, for example. It's not a web page, of course, but it's something that is inherently without outlinks, or it could be a PDF, or it could be just a plain text web page. So we cannot have any outlinks here. And what we can do is basically some mental transformation that basically zeros in the row are the same as taking even probabilities of transition. And this is called random surfer in the terminology of creating PageRanks. And basically it says us that if we get here, just imagine a person who is browsing a web graph. So a user that uses just the web browser and is clicking on hyperlinks and just browses the web graph. And as we said, we can see this as a transition probability from here, from P3 to something else, to P1 to 5. So the user can choose one of the three. But if the user is in dangling node, here, in 2, then the user cannot click anywhere. The user is stuck, basically stuck. And what the user in reality does, in reality, if you are stuck on a web page that does not have any outlinks, what you are doing, you basically reset your search. So you basically randomly go to any of the pages, right? So in this situation, it is not so harming operation if we, instead of no inlinks, we create, in case of no outlinks, we create all of the outlinks that could be created for the node 2. So we get the outlinks to all of the other pages. So instead of all of the zeros, we get 1/6 in all of the positions here. So this is basically what is compatible with the random surfer. If the random surfer is here, then the random surfer goes randomly to any page. And that's the same as if we have 1/6 here. There are possibilities to go anywhere. So this is the operation that we get. So we insert into the 0 rows non-zero rows that are just this E, this is unit vector. So there are only ones, but they are divided by n. So we get, for example, 1/6 in the example. And that's how we obtain the stochastic matrix. Here it is the formula, how we obtain the new matrix. So we start with the H, which is the original matrix. And then we add to this matrix another matrix that we get by multiplying two vectors. A is a vector called so-called binary dangling vector, and it's a vector where it has 1 at position of a page PI that has no outlinks. So in our case, that was just one node, and otherwise other positions are 0. So we get matrix here that have non-zero rows only in place where in H there is 0 row. So we just sum these together and we get what we need to. So in the example we have this 0 row, and we have another matrix that only creates this non-zero row, and we add these together and we get the matrix S. So it will be the stochastic matrix S. So now we have stochastic matrix because the non-zero rows that were already non-zero here were already stochastic. And we added more to the 0 rows. So now all of the rows are non-zero and the whole matrix is stochastic. Okay. Now the matrix needs to be also irreducible and aperiodic. And these two properties could be basically obtained by enforcing a stronger property, that is primitiveness of a matrix. Once we force the matrix to be primitive, it will be also irreducible and aperiodic. And the definition of primitive matrix is quite simple, because it just says that for some k, for some number k, the power to k of any element of the matrix must be positive. Basically, this says we need a matrix that has no zeros inside and everything there is positive. So what we need to do is to turn the metric S into some other matrix where there are no zeros inside. That's what we need to do. So finally we get the Google matrix, because that's what we get after we turn the matrix S into the other matrix. And the matrix will be called G, like Google matrix. And it will be composed of the matrix S and some basically noise matrix, because this is unitary matrix. This multiplication is one unit vector, second unit vector transpose, vector multiplication. We get unit matrix, so there are only ones in this matrix. But we divide all of the ones by n, so we get basically stochastic matrix, but completely uniform. And we will add these two matrices, the S and this normalized unitary matrix. But we will weigh this sum by a parameter alpha, that is basically between 0 and 1. And this parameter allows us to set what is the proportion of the noise. I will call this a noise, and basically not noise, the adjacency matrix we already had. And what we get is basically completely dense matrix where there are no zeros and only positive numbers. And we can, of course, tune the alpha to get more or less noisy matrix. And why we are doing this? Basically, we are changing the semantics, because now we have no zeros, but we have positive numbers. And is it okay or not? So is the adjustment from H to G natural? So we already talked about the random surfer for the case of the stochastic matrix, but now we can extend it also to the G matrix where there are no zeros. So again, think about a random surfer that goes, that clicks on the links within the pages and just browses the graph. And as I said, in a dangling node, it just can click anywhere, because in dangling node there is no outlink. So there is the randomness of the surfer, because in dangling page there is random, or generally random, arbitrary decision of the surfer. But not only in the dangling node, but anytime in any page, from time to time, any surfer can just say, well, just following links is too boring. I need to go somewhere else, completely elsewhere. And the surfer teleports randomly anywhere. And this is basically the semantics of adding very small numbers in the place where there were the zeros. Because the zero meant I cannot get there. If there was zero, it was transition probability matrix, and there was zero probability, so I cannot get there. But if we extend the concept to have also random surfer, I can go anywhere, but with different probabilities. And if the parameter alpha, as we can see in the formula, if the parameter alpha is close to 1, then there is very little of this noise, because then there is 1 minus almost 1, and it will be very small numbers here. So we almost have the zeros in the zeros places. But if we have alpha that goes more towards 0, we get more noise here, and basically we allow more randomness in the random surfer concept. But this is a matter of definition what we are modeling. So if we model browsing of web page, including a kind of randomness, then this is okay. And then the adjustment from H to G is basically natural. So This is the explanation for the transformation to G. And then we get G that is stochastic, aperiodic, and irreducible. So now it's in the form that basically guarantees all of the questions to be answered positively as was asked. Okay, so now we have the desired famous PageRank formula that is again in this iterative form. If we expand the G, we get this expanded form, and we can even expand S to the H matrix, and everything is cool. But is everything solved? Well, it's not. Now we need to really think about how to compute basically the PageRank vector. Because now we have G that is very dense, basically super dense. There is not 1 0 inside G. So just remember when we were talking about inverted index in case of Boolean model and vector model, we were relying on the sparsity of the matrix. Otherwise, we could not use the inverted index. And now here, this is similar. If we have a very sparse matrix, then the multiplications of very sparse matrices could be done very quickly. But now we have G, which is super dense and could be super huge because we have billions of web pages times billions of web pages. That's the G matrix. And that's very bad for computation. So this is what we need to address. Next, the iterative process converges, and it's empirically confirmed that it is enough to have 50 to 100 iterations of the process to get enough precision of the page ranks. So it kind of converges. And the good is that there is really just one PageRank vector pi, and it doesn't matter on the initialization vector pi in the 0 iteration. So we can do any initialization, and we get just one PageRank vector. So that's good. And all of the numbers in the PageRank vector are positive, and there are no ties caused by zeros. So this was the problem of the rank sinks. There were many zeros, so there were ties. So this is not with the G matrix. Now the parameter alpha was observed that it works best for 0.85. This is really empiric value reported by Google that it works the best. So there is something like 15% of randomness or of noise in the Google metrics. Basically, it means that if a surfer, if a user that surfs that browses a web page is on average 15% of decisions are random, and 85% are following the possibilities of the hyperlinks, which basically is possible. Why not? There's some psychology behind the random surfer, and it worked best. And if we return back to our example, we basically get the final ranking, final page ranks after a number of iterations, and we get these page ranks for all of the pages. So the winning one is 4 with 0.37. The next is 6, 0.28, then 5, then 2, then 3, and then 1. We can see that there are positive numbers everywhere, so, and there are no ties, so it's nicely ordered from the greatest to the lowest score. So we have good distribution of the scores. Okay, now how to compute that? As I said, we have now super dense matrix G. So materializing, so really storing the matrix G and computing with the matrix G directly, it's impossible because of the size of the web. So the direct methods cannot be applied, and even 12 years ago we basically had Google metrics that is billion, or not billion, thousands of billion times thousands of billion, and it's not feasible to really store, not even compute with that. So we need to use other methods for computing PageRank, and these methods are called basically power methods, and these are matrix-free methods. And these methods basically work with the expanded form of this formula. So we have not the matrix G, but we have the original matrix H, basically. That is very sparse. And it's so sparse that we can basically think about the matrix H as about a vector, because there could be something like 10 non-zeros per row. So we have basically something like 10 vectors. Instead of a matrix, we have 10 vectors. Of course, there are different dimensions because it's not on the same positions of the values are randomly distributed in the matrix, but in the quantity, it's something like 10 vectors. So, yeah, this is necessary condition. So we cannot afford to do matrix times vector computations. Even the vector alone, that is just the PageRank vector, is a huge amount of data, some terabytes, because if we imagine this is thousands of billion of numbers. So just multiply it by some float and you get the really huge volume of data. So these power methods, so the power method basically computes with the expanded form of the formula. And what we can see here, there are only vector to basically vector multiplication, because H is extremely sparse, so it's almost a vector, or it's like 10 vectors. So we get vector-vector multiplications. Here we get another vector-vector. H is the vector of dangling nodes. And again, we have here a vector. So we don't have any matrix to vector computation. So this is this matrix. That's why the method is matrix free. Okay. And other concerns is that, for example, 50 iteration is quite good. So the whole computation takes just 50 times some linear time, where n is, of course, number of web pages. And it is also very interesting result that we basically need, if we want to have accuracy of PageRank to t digits, it's enough to have this number of iterations, so minus t divided logarithm on base 10 of the alpha parameter. So that's why we need just 50 iterations for, let's say, 2 to 3 digit accuracy. One could say, well, 2 digit accuracy is not much, because if we just imagine we have billions of pages and we have only 2 digits of accuracy, that means basically we have only 100 of buckets where all of the pages must be put into. So we have just very low resolution of 100 of categories, because they are just 2 digits, or 1000 if we have 3 digits. But you must take into account also the other scores that come with the querying, for example, cosine similarity for the vector model, and we must take into account the aggregation of page ranks and the content ranks. So we basically get many more than just 100 or 1000 of resolution of the overall rank. So that's why we are okay with just 2 to 3, because we suppose we will combine it by other scores like cosine similarity. Okay, so this was basically the basics of PageRank, and there are many other topics that are related to PageRank computations. There exists a book on this topic, and there are very important questions that are beyond this course. For example, similar to the topics that were with the vector model. For example, computing PageRank for a collection of web pages is okay, but we basically have a web which is dynamic structure. it changes every second. So to have up-to-date PageRank vector for all of the pages, we need to really repeatedly recompute the PageRank vector. And it would be really time-consuming to do this recomputation from scratch, not using the already computed PageRanks for other snapshot of the web page, web graph. So the very important topic is how to update PageRank vector that was already computed, but some pages in the web changed. So how to update this change to the PageRank vector. Other topics are accelerating of the computation of PageRank, large-scale implementation of PageRank, and also the sensitivity of PageRank, because the many parameters that we are using in PageRank computation lead to different behavior and different convergence, for example, and so on. So studying the sensitivity. And last but not least, what about the alpha factor? So how the alpha is important. We said it was set to 0.85, but what happens when it is 0.9 or 0.7? So all of this is a subject for further study. Okay, so we basically finished. The last topic is just this slide. You can use this web page, prchecker.info, where you can just observe the page rank of a page that you like, and it gives you some score. And even here we can see that we have just one digit of PageRank. We have just 0 to 10 levels. But as I said, because we combine the PageRank score with some content score, it's basically okay. It's just a very rough classifier if a page is completely garbage or it's very relevant. And the spam resources or spam pages are just disqualified with 0 PageRank, and this is why there are no spam pages returned to the user when searching, because their PageRank is just 0, so they cannot become into any position of the ranking. Okay, so that's it for PageRank, and we'll continue with the next lecture.